We are building the bit by bit project from the YByte Python curriculum available at www.ybyte.in. So far, we have been exploring the different bitwise operators and or XOR, left shift, right shift, and so on. We see that some of these transformations are quite interesting, and sometimes we are able to even find equivalent arithmetic operators for these. And we also saw some special cases, let's say for AND or an XOR. Now, before moving forward, I thought it may be fun to sort of visualize some of this in a very, very unique manner. So what we are going to do here is that we're going to apply the knowledge that we have gained so far and let's say these functions that we have been exploring to gain a better feel. We will apply all these ideas to a black and white image, which is also known as a monochrome image, because this will give us a visual angle to our learning. And sometimes seeing is believing. When you see something in front of you, somehow the whole meaning starts to make sense. Um, so what we will do, we will pick up a raw black and white image and we will read that into Python. Now this itself is quite interesting. The pillow module, also just called a PIL. With this, you can do a lot of stuff with images. So that's something we can explore also. We will get the pixel values into a list and then we will apply bitwise operator to every pixel to, let's say, create a new image with the revised pixel value. So for example, I'll take every pixel and modify it with some kind of bitwise operator. I get a new pixel. I will create a new image with these revised pixels and I'll compare these two. And giving, let's say, this comparison creates a visual dimension to our learning, because then we can see the impact of various operators that we have been doing. And I think this is quite interesting. Now, the image that we are going to use for this purpose will be this cat image. Now, this cat is very cute actually. The reason I chose this is because it's also very expressive, because the eyes kind of talk to you, and it's also got a nice, let's say, range of colors in there, right? So there's white background and then it's like a little bit blackish grayish cat. We are going to read this into our Python program. I'll show you how to do this later on. The interesting bit is that every pixel, basically this is made of many, many pixels, kind of like a very dense pixel art, you can say. Every pixel has a value between 0 and 255, which is why it becomes interesting to us, because think about it, 0 and 255 means that every pixel is basically an 8-bit number. And I could apply the operators that we have been learning all this while to, let's say, this image. Now, as I said, the pixel values are between 0 and 255. It turns out that 255, it, it turns out that 0 is the darkest, or let's say the most black, that you could have. And 255, on the other hand, is white. Everything in between is, in fact, shades of, let's say, gray, you can argue. So white, a little bit grayish, little bit grayish. You can see it's continuously becoming more and more gray, and then it becomes totally, let's say, black. In fact, this also tells you how binary numbers work. Till about 60, still about 32, everything looks almost the same, and then you start seeing a sudden change with every increasing bit as we move forward. So 64, 128, 192, 224. So you can see this is all changing. Now, what does this mean for our image over here? Well, pixels that are, let's say, in this zone, which are all white, are probably close to, let's say, 250, 255 and all that. Pixels that are very dark, close to, let's say, the cat's nose, or let's say on her forehead, they are dark black, and hence they are like close to 0. Now, when we do, these bitwise operators, these values will change and we'll be able to see it very, very vividly over here. So, I read this image. I read this image using, let's say, this library called PIL, and I import image. I just basically convert this into L. L means luminescence, which means I'm reading this like a monochrome image. Now, these are some details of the library. You can explore this, but basically, this gets me an image read into Python, and I convert that into a list, because then I get numbers. The entire image is available to me as numbers, which can then be manipulated to create a lot of effects, as we'll see. So just the pixels list. Well, I've got 100 times 100, which is 100,000 pixels. The minimum value is 23 and the maximum value is 254. So we can see it's quite, let's say, white, almost white. And if I look at the raw pixels list, it's like numbers between 0 and 2. Now, like I said, we will run a for loop, in fact, a nested for loop, to apply some kind of an operator to each and every pixel. And we will see the impact of that visually, which I think is really quite interesting. As in order to do this, I'm going to convert this image from 1D to 2D because the list is one dimension, but image is in two dimension. This is just the way we are, let's say, handle the pixel art project. So I can basically pixels 0 to 99 are row number one, row number zero, let's say, then row number one, row number two, and so on and so forth. Just the way we set up the for loop. I end up with, a for loop where I'm just reading these pixels and I'm creating a new image here with the modified pixels. So just for a, now having modified every pixel value, we can use the put pixel method as shown below to create the new image file. Now I wouldn't want you to get too trapped in, let's say, the dynamics of this. The idea is very simple. This is like a nested for loop, almost the same as what we were doing in, let's say, pixel art. So I'm going, let's say, row by row or perhaps column by column, and I'm just figuring out what pixel I have to put at, let's say, this specific KK and JJ. Now this may look a little bit strange, but really we are just putting pixels at, say, JJKK. You have to experiment this a little bit to get it correct, but this works. And then I can save the file. So let's just see how this thing works out. My original image was, let's say, was this. It looks quite blurred when I zoom it out. If I just don't do anything, if I just leave the pixels, let the pixels be, I just put the same pixels back, obviously I get back the same image. There's no difference. Now let's say I take every pixel and I go and that with all zeros. Remember, 0B0000 means basically a zero. Recall that when I AND a number with 0, the result is also 0. And we see that in fact here, every pixel after ANDing with zeros becomes a 0 and hence totally dark. And when I look at my new image, in fact, that is all zeros. I will later on demonstrate this to you as well, so that becomes a bit more lively. But basically, the reason that the reason every pixel became 0 and hence dark was because we did a bitwise AND with all zeros here. Of course, we can try masking only parts of the image so that, maybe only, let's say, the eyes are seen, everything else is blacked out. That will be pretty cool. Likewise, if I do an OR with all ones, remember, OR with all ones of 255 results in a value of 255. The image becomes completely white because every pixel basically becomes 255, which is the brightest and hence white. If I were to do an XOR with all ones, now remember, XOR with all ones was kind of like an inversion. I was ending up from 200 from the value to 255 minus the value. We saw this in the special cases. This looks pretty cool. Notice all the whites have become, this looks pretty cool. You notice that all the white areas have in fact become black. Black areas, for example, let's say this line has become white, as well as the cat's forehead has become white. There is an inversion going on. Pretty interesting. It looks like the negative of the image is being seen, right? And all we have done is then on every pixel, I've gone ahead and done an XOR with all ones. Now you might argue that, look, I could have done this also by just doing 255 minus pixel. Yes, you are right. But this is kind of giving you another way of looking at the whole problem. Let's say I right shifted every pixel by 2. Now remember, right shifting is kind of like division, which means that every pixel I am making smaller in value, which means that I am making every pixel darker. And this is indeed what happens. It looks like the light has been turned off from left image to the right image. The whole image seems to have become darker because I have done a right shift by 2. Again, we can do this on parts of the image. Basically, every pixel is becoming roughly 4 times smaller in value. And hence, this is what we are seeing. Again, floor division would have been equivalent, but this still gives an interesting viewpoint. If I did a left shift by 2, in fact, on the other hand, the image becomes completely bright. The areas which were quite grayish earlier now become whitish. Of course, those which are very close to 0 just become gray. So you can still see some outlines of a cat, but looks very different. Looks like overexposed, over like too much light falling on the cat. We can't quite see it, right? But that's really because we are left shifting by 2. In fact, I'm doing a little bit more. There's this function I've created, which is also clipping the value to 255 so that I can render that in the image. Yeah, but that's what it is. Now I can do some more exotic things because all of this that we have done so far, you could argue that, I could have multiplied, I could have just division and a floor division, but we can do some very interesting operations. For example, if I, let's say, modified every 7th bit to 0. Now this is very, very interesting actually. Again, makes you think about binary numbers. Basically, when I'm doing an AND with 0 followed by all ones, effectively I'm making the leftmost bit become 0. What that means is that all the pixels that were higher than 128 became darker and rest remain unchanged. So this in fact tells you, look, this background was definitely higher than 127. It became darker. A large part of the cat was quite bright. Hence, it was more than, let's say, 128. Now, when I look at it, it has become darker. The parts that were reasonably dark to start with are unchanged. So cat looks quite different in this. Looks to be probably from a different variety altogether, right? Uh, very, very different. Yeah. Again, we can do this on parts of the image. Here, I made the seventh bit 1 because I did an OR with 0, 1, 0, 0, 0, 0, 0, which means basically what's going to happen is that every pixel, the seventh bit will become the last bit will become 1, which means that the darker pixels which were lower than 128, remember those are the ones where this bit was 0, those pixels that were darker have suddenly become a lot brighter. The bright pixels remain unchanged, and again the look and the feel of this completely changes. Those areas where it was dark are suddenly bright, everything else remains unchanged. The whole image starts to look totally different. In fact, we can do more exotic things as well. So here what I've done is, now this is where pure bitwise operators, basically I've just said, okay, let me just go and swap the 0th and the 7th bit of every pixel. And this is actually quite interesting because now notice we can see the outline of the cat, but the whole thing is quite highly randomized. Basically, some pixels have become brighter, some have become darker. And in fact, this, when I look at this, you know, basically it kind of tells me that, look, this could be used to even send some kind of a secret messages, right? If I do some manipulation at the bit level, unless we know what exactly has been done, it could be quite hard to go from here to here. Whereas from here to here is very simple, right? So this is quite nice. Uh, Similar function, if I go and reverse, let's say every bit in a string. So basically 0, 1, let's say 0, 0, 0, 0, 1 becomes 1, 0, 0, 0, 0, and so on. Reverse every bit. Again, this is done using bitwise operators. The whole thing looks completely different, right? So the point of doing this is to make this whole learning more vivid, more visual, because left on their own, these operators could be a little bit, abstract. So I thought this could be a nice detour. Before before wrapping this up, let me show you, some of this sort of live. So, let me show you the grayscale image first. So here's the grayscale image that we were looking at. And in this function, I've got all these. For example, mask of, let's say, 4 is going to right shift by 2. If I were to do that, let's say I put mask is 4 and I run my code, let's say. So now I just go and let's say when I run this, so this was my original image. Now the modified image is this image, which has become much darker. In fact, we can play with this. Let's say I right shifted not by 2, but in fact by, let's say, 4. The whole image will be almost completely black. We can see this, in fact, when I run this piece of code, and I look at my test OP, it very hard now to discern that there's a cat over there. The whole thing has become dark, and not surprised because that's what we have done. Let me just set this back to 2. If I were to do, for example, let's say an XOR with, let's say all bits being 1, that's an inversion. We can again see that. So that's my mask is, let's say, equal to 3, right? So when I run this piece of code, I expect the image to become negative, and that's indeed what has happened. This is where I started, and this is what I am ending up with, right? So really quite vivid. You can see that every pixel has basically got inverted, right? So really quite interesting, I thought. This file is available to you. You can play with this. You can come up with your own masks and actually create some interesting insights as well. I hope you found this interesting. In, in fact, what we have just seen is some very, let's say, elementary image processing, which is where the idea is that we take digital images and apply algorithms on them to make them, let's say, sharper, to understand it's a vast field in itself. And I hope that this little introduction got you excited about this field and also made this bitwise operators a little bit more visual, a little bit more vivid to you. In the next video, we will start building the LED patterns activity. And that's when all of these concepts will start coming together. Now, that is how we learn Python programming at YByte. Build activities, understand concepts, build activities, and have fun. Look at our website www.ybyte.in because we have many, many, many such activities from which we can learn Python. Take care. Thank you so much. Bye bye.